Hi, and welcome to the Mayfield Renewables course on the National Electrical Code and solar systems. This is the first part of 3 that we're putting together for a long course on the NEC and specific to solar and the interconnection methods for our PV systems. So really big focus on Article 690 and Article 705. So that's going to be really the big main focus of this class. We have other classes where we get into energy storage, codes and standards around that. So this one we're going to just take a deep dive into 690, 705. And in this first part, we're really going to look at a few things on the front end of code, and then we'll jump into 690 and kind of do those front few sections before we jump into the back end and then Article 705 in the other parts of this course. So you're going to use the lowest expected ambient temperature for your location, and you're going to then adjust the voltage based on that temperature. So the first option that we have per the list of ways to calculate this is to use the module manufacturer's information. And you see here on the screen, if you can see in that bottom right corner, we have from a module manufacturer, we have what the temperature coefficient is for the open circuit voltage. In this case, it's 0.26% per degree C, negative 0.26% per degree C. So that negative value indicating that inverse relationship with temperature. And so what this is saying is that as the temperatures increase from standard test conditions, or 25 degrees C, the open circuit module voltage will actually drop by about 0.25% for every degree C that it rises above 25 C. Conversely, for every degree C it drops below 25 C, then your module voltage is actually going to raise about 0.25%. So we have to take that into account, do that math in order to understand what is the maximum voltage based on our location. So we found a location where it's negative 10 degrees C is the lowest expected ambient temperature. We have a module voltage, the open circuit voltage from the spec sheet, and we have the information from that same spec sheet what the temperature coefficient is. So in this case, we have a difference of 35 degrees C. So because we're in a location where the lowest expected temperature is negative 10 degrees C, standard test conditions are 25 degrees C. So we are negative 10 degrees C minus 25 degrees C. That tells us that we have the potential for this circuit to operate 35 degrees C less than what the standard test condition temperature of 25 degrees C is. That's how we got to negative 35. The negative 0.26 is straight from that spec sheet. And again, those negative symbols are important because the negative 35 is indicating that we are 35 degrees C less than standard test conditions. The negative 0.26 is indicating that inverse relationship with temperature. So we take the negative 35 times a negative 0.26, and that tells us that we're going to see about a 9.1% increase. Negative times a negative is positive. So we're going to see an increase of about 9% from that module's standard test condition voltage. So that value from the spec sheet was 45.3 volts. We're going to move the decimal place over a couple places to do our math. So 45.3 times 1.091, or to indicate a 9.1% increase, tells us that in that location, for that temperature, that circuit will actually be 49.4 volts.